So yeah, just a couple announcements. So Eric's flight got delayed, so I'm the guest lecturer, last-minute guest lecturer. So apologies in advance, because these slides are made by Eric, and any mistakes in the slides are Eric's fault, not me. And homework 1 is due this Wednesday, right? And remember, there's no, so the deadline is strict, so submit anything you have at that point. Don't wait until you have a perfect solution. Okay, no more announcements. So let's get started. So today's lecture will be on variational inference. So we talked about the basics of variational inference last time, and then covered some of the applications in latent tertiary allocation model. And we're going to see a little bit more advanced variational inference technique today, also applied to latent tertiary allocation model, but it generalized to other models as well. So those are the stochastic variational inference, and also later on talk about Blackbox variational inference. And then after that, we'll talk a little bit about the theories behind variational inference. So we're going to discuss what actually does the mean field method or other belief propagation methods do in a higher level. And there's a unifying theory that encompasses all of them. Okay, so last time we talked about topic models, are models of collections of documents, and then where the word, we ignore completely the word sequence information, and then we just do a kind of mixture model, but mixture on top of mixtures again for the words. So this model, as specified, is very nice, but the inference, of course, is pretty hard, as always the case for many latent variable models. So we cannot do exact inference. So the method we take last time was to do approximate inference and specifically variational inference. Okay, so and even more specifically, we took mean field variational inference, which corresponds to the right-hand side diagram over there. Okay, and if you just optimize the evidence lower bound you derived from mean field variational inference, it'll just be coordinate descent over mean field variational approximation parameters. So you fix all the other parameters, and then you choose one parameter to optimize, and then you do this over all the parameters. So in optimization, that's called coordinate descent, and here it's the same thing. So you do iterate over the whole parameter set many, many times and until convergence. Okay. Usually in latent variable models, or as well in latent tertiary allocation, there are two types of parameters associated. One is per data point parameters, and then the other is a global parameter. So in latent tertiary allocation, there's a global topic parameter beta that's affecting all the different documents and all the different words. And there's also local per data point parameters, theta and the variational parameter of theta, that's acting only on a particular document or a particular word. So those are the per data point parameters. So if you abstract that out, if you just look at what's the difference between global update equation for the global parameters and the local parameters, it kind of looks like this. So you first iterate over all the data points and then update their own associated local parameters. And then after that, you use all the sufficient statistics you collected before to update the global parameters. But of course, this is not very viable if the number of documents, D, is very large. Like if you have millions or billions of documents in the internet company, then you don't want to do the inner loop for a very long time and then only update the outer loop once after like 10 minutes, right? So you want to update your model frequently enough to capture the to make the model better at any point. So what you can do is to use some kind of idea similar to stochastic gradient descent. So you can first separate out the loss function into two terms. So you can separate out the global parameter part and then the local parameter part. And so the resulting decomposed loss function looks like something in below. So the f lambda is the global loss function for the global parameter, and then gi is the loss function for the local parameters, and I is the index for the data points. So what you would do is we would first maximize or optimize for the local parameters first, because the f of lambda doesn't depend on I at all. So you can just push the maximization in and then do the local maximization first. And typically this will have a closed form solution, or it's very easy to solve because it's just related to one data point, and it's usually considered very cheap operation. And then let's say the maximum value or the argmax really should, you see a mistake over there already. So it's not my fault again. So that should be the argmax of that is phi star. And let's plug in phi star and then take the gradient for the global parameter lambda. And that'll have the form of some gradient plus a sum, average or a sum of n items, right? And this is the same situation we encounter in gradient descent versus stochastic gradient descent. So we can do the stochastic approximation for the second term and obtain an unbiased estimator of the gradient. So that's the basic idea of stochastic gradient descent, stochastic variational inference. Okay, so in hindsight, it should be very clear, right? And if we do stochastic updates for lambda, then we might as well just optimize for one local parameter, let's say phi of I, and then do the stochastic update for lambda, and then do choose the second data point, phi of j, and then do the global parameter update for lambda again. So that way we can update the model frequently enough to make the convergence faster. So that's what we mean by online here. There is something orthogonal to this issue, which is natural gradient. So let's see. When we are doing variational inference, we're optimizing an evidence lower bound, or we're optimizing some quantity related to a distribution. But the thing we're optimizing is minimize or maximize over parameter theta distribution parameterized by theta, or some function of this, right? The issue with here is sometimes the distance between distributions is different from distance between parameters. What do I mean by that? Recall gradient descent is gradient descent for function f of theta is motivated by some first order or second order approximation. So we expand this function at theta 0 and plus first order term right, and then there's a second order term okay, this is what gradient descent does, and then essentially to optimize a function like this at, let's say, theta, and then at this point, this is theta 0. We're currently at theta 0. And what it does is it forms a local quadratic. So this is a local quadratic approximation given by the Taylor expansion, and we choose the minimum of that local quadratic and call this to be our next update. So this is how gradient descent is motivated, right? What it essentially does is there should be a second order term here, right? What gradient descent essentially does is treating this as 1 over t times identity. So it uses the 1 over t times identity as a proxy for the second order term. But now what I'm saying is this approximation may not be very good for distributions because, for example, let's say there are two Gaussians like this. Let's say this is 2 distance apart, 2 units of distance apart. There's a very sharp Gaussian distribution. There are also 2 distance apart. Their mean are 2 distance apart, but their variance are very different. In terms of parameters, let's say the variance term is fixed. In terms of parameters, we are only left with mean parameters, right? The distance between these 2 Gaussian, the distance between the mean of these 2 Gaussian are the same as the distance of mean of these 2 Gaussians, right? But their KL divergence is very different from these KL divergence. So the distance between parameters are very different from distance between distributions. So this is what we should take care of when we're optimizing some objective function related to a distribution, related to a parameter of a distribution, right? And so even crazier example would be, we know a Gaussian is, let's say a mean zero Gaussian can be parameterized by its variance, right? But it can be also parameterized by the inverse variance term. So there could be totally 2 different kind of parameters for a distribution that follow very different scales. Like variance 1 and variance 2 are 1 apart, but inverse variance of 1 and 2 are not the same as variance of 1 and 2, right? So they're different. Their distance should be calculated very differently, even though they represent the same thing in the distribution space. So one sentence summary would be distance between distributions are different from distance between parameters. And the naive Euclidean geometry for the parameters is not the best to do when we are trying to optimize the parameters of the distributions. Okay. So that's how this thing called natural gradient is invented. So what natural gradient does is essentially we don't use this term, but instead we use the feature information matrix, which is negative of Hessian of log likelihood. So it's essentially using this as the second order approximation. And then once you plug in and sort it out, it'll become something similar to Newton methods for the Euclidean geometry update. So it'll be something like the big capital G here is the feature matrix, feature information matrix. So it's going to be like the second order term inverse times the original gradient. So it's taking into account the local curvature information. Okay, so that's the natural gradient. And yeah, so this is just you plug in natural gradient into stochastic variational inference, then you get some even better algorithm. So not that important. Okay. Any questions until now? Okay, so there's then I'm going to talk about a different set of very recent. I don't know if it's appropriate to call it recent. It's invented in 2014, 2015-ish. So these type of variational inference methods are called Blackbox variational inference. They are mainly motivated to account for the situation where your model is not conjugate. So if we remember, in the LDA case, or in if you apply for many other classic examples like Gaussian mixture models and so on, the good old variational inference relies a lot on the conjugacy between the likelihood and the prior function, prior distribution. So for example, if I choose likelihood to be multinomial, then my very convenient choice for the prior is Dirichlet, because those are conjugates. So my posterior also follows a Dirichlet distribution. And if I choose, for example, Gaussian, and that my prior for the mean would be another Gaussian, and those two multiply together is another Gaussian, things like this. But of course, there are many. Conjugacy is just one convenient choice that makes calculation easier. There's no motivation. Well, there's very little motivation for whether it's a meaningful choice or not. So oftentimes you want to use some specific prior that's not conjugate to your likelihood. Then what do you do? And all the machinery we have developed so far sort of breaks down. So, but now we can use Blackbox variation inference to mitigate this problem. So the big idea is to have a black box. Nowadays, black box is just a neural network, let's say. And then if you give any forward model, like if you gives the generative logic of a stochastic model, then, and if you throw the data in it, then it'll output the variational distribution. So it's kind of, it might kind of sound crazy, but let's see how it goes. So what it does is whatever model you specify, it'll use the neural network to translate to output the evaluation of your variational part. That's data I. The evaluation of your variational distribution. And this Q is parameterized by a big neural network that's very flexible. So there are mainly two types of black box variational inference I can talk about today. One is called score gradient, and the other is called reparameterization. So suppose we have the evidence lower bound defined as the expectation of log joint log of prior, right? This is just the same as before. Right now we're talking about a general abstract latent variable model where x is the observation and z is the latent variable. And then by specifying a generative model, we specified how this looks like. Okay? Now and then we're endowing a variational distribution Q parameterized by lambda for z. And our goal is to do inference on Q. Okay. Now, in order to update to optimize for this Q, we need to find the gradient with respect to lambda, right? So we need to do this. Okay. So now that's where these two distinction comes from. There are two general ways to derive to represent this gradient of elbow with respect to lambda. So the first thing we can notice is, let's see. Can you say what's this? Anyone? You get a bonus point. It is just two composition, right? So use chain rule. Okay, so if I use chain rule for log, then it will be 1 over this. Okay, and then what's inside? The inside is just going to be this, right? Okay, make sense? Now, the second thing we need to know is so this thing is called the score function in statistics. And so in words, it's just the average log likelihood gradient is always 0. This is a very neat proof. I'm not going to cover that. You can find this pretty much in any statistics textbook. Okay, so with these two in mind, let's see what it looks like. So it's Q lambda Is it right? That's right. Okay. Now I need to take derivative. So you can just, because lambda and z are not dependent, you can push this in. So what's the derivative for this? This term doesn't depend on lambda at all, right? So it's constant. And we're just taking derivative with respect to this, right? So, okay, that's the first term. And the second term is this. So what is this? It's just times this. And the second term is the derivative of this, right? So we have it over there. Okay, and everything with tz. So far, so good. Okay, now let's notice. This thing has this term in it. This also has this in it. And this also has this in it, but we already see this term cancels out. So if we kick this out, then is it going to be minus? Yes. Okay, right? Now, this still looks kind of mysterious because it's an integral of a gradient-looking thing and something else, a bunch of things. Now let's plug in this. Okay? We know this part, right? So if we multiply this to the left-hand side, then what's this? This is equal to that, right? Because of this identity. We just multiply this q of z to both sides. Then that's why we obtain this. Then a bunch of things in the bracket. But also there's an annoying -1. Let's look at -1. So something minus 1 dz, right? Okay, so now do you notice something? So this is a distribution of a bunch of something else, integral of distribution multiplied by something else. So this is in the form of an expectation of Q. So this term is equal to a bunch of terms minus 1. Do you see that? Blink your eyes if you see it. Okay? But we're still off by minus 1, right? So where does minus 1 go? Yep, right. So who was that? Okay. Let me know your Android ID after the class. You get a bonus point. Okay, so because the score function is 0, then this minus 1 term is 0 in the equation. So it goes away. Okay? So now that's how we arrived at that. So what we did so far is to represent this as an expectation of something. To see this expectation, you should notice we can use Monte Carlo approximation or to do a approximation of the whole integral of the whole expectation. So that's essentially what this original BBVI paper does with score gradient. Okay. Thank you. Okay. So this is also in reinforcement learning. This thing is also called the reinforced gradient estimate. Just so you know, it goes by different names. Yeah, but the only drawback is this estimate. If you do Monte Carlo estimation of this expectation, then it will usually be of high variance. There are some proofs in it. It's not very rigorous, but you can sort of show. So there has been a lot of work since then to reduce the variance, like to do raw Blackwellization or add control variates and so on. So I talked about there are two general ways to estimate this gradient, right? This score function gradient is one thing. And the second thing would be reparameterized gradient. I don't know if I should go into that. Maybe you should go into that in the VAE lecture. So this is essentially the core idea behind the variational autoencoder. So in terms of variational inference, you should just notice that this different kind of gradient estimator, different from score gradient estimate. Okay, so it just relies on some representing the variational distribution as some transformation of simple random variables, and then make use of the differentiability of the transformation to perform gradient estimation. Okay, so I think that's the first part of today. Any questions? Let me know. Oh, sorry. There should be this multiplied by this thing in the square bracket. So 1 is just going to be expectation of this. Right? Okay, then that's 0. Okay. All good? So we're going to talk a little bit about how mean field and other type of variational inference methods come under a umbrella theory that unifies the view for all of them. I don't think we covered loopy BP, right, in the class. No? Okay. So we only talked about BPs and then BPs for junction trees and not loopy BPs. Okay. Loopy BP in one sentence is just applying BP no matter what you have. So we know BP only gives you exact solution correct solution when the graph is a tree graph, right? As an example, the homework problem on HMM is a tree graph, right? HMM is a tree, right? So that's why you can use the belief propagation algorithm. But when the graph is not a tree, can we still apply BP no matter what? So that's the intuition behind loopy BP. So if the graph isn't a tree, it means the graph has a cycle. So BP is not gonna finish in finite amount of time. It's gonna keep sending messages along the cycles. But people found this often works. They didn't know why for a long time, and later on, some people provided some theories, and this is going to be one of them. Okay, so last time we've seen this. The variation method is a general term appear everywhere. If you have something that's intractable or hard to get, you can express it as an optimization problem and then try to solve that optimization problem instead. Sometimes it makes problem easier. For example, like getting the top eigenvalue of a matrix, you can just solve this Rayleigh quotient. And solving linear systems of equations, you can also, instead of inverting the matrix, you can formulate as an optimization problem and then solve it iteratively. So yeah, let's do a little bit of recap. So let's think about undirected graphical models, because in the inference setting, BNs are basically the equivalent as a Markov network once you convert it to a causal graph. So let's consider Markov random field for now. And then the quantity of interest often in the inference setting is the marginal distributions, like on one dimension. Or sometimes we have to do inference on the pairwise distributions, like in HMM, we are querying one singleton marginals and then pairwise marginals, right? And we sometimes also need to get the normalization constant, or sometimes called the partition function, Z. In HMM, we are also performing this normalization function as computation. That's what you're doing. But to represent these two queries, the marginal distribution or the pairwise distribution and the normalization constant as a variational problem or an optimization problem, we need some vehicles. Like today's vehicle is going to be exponential families and convex analysis. So let's recall exponential families. So for a n variable, m-dimensional distribution, n-dimensional random variable, its distribution follows a exponential family if the density function can be written like this. Expectation of a linear function minus some normalization constant. So theta here is called the canonical parameters, or sometimes called the natural parameters. It doesn't depend on x. And the only part that depends on x is in the sufficient statisticity function. So you can think there are like d functions. So the phi of x is actually a collection of d functions, phi1, phi2, phi3, all the way to phi d. And correspondingly, theta also has d dimensions, right? And A's role is basically just to make things normalized. So you can view it as a log normalization constant. Sometimes it's also called the log partition function. In the latent variable model case, it's also equivalent to the data likelihood. Okay? And one important thing in exponential families is whatever the exponential family distribution you have, the log partition function A is going to be convex function. You can prove this by looking at its Hessian. Its Hessian is going to look like a covariance matrix, and you know covariance matrices are positive definite, so this function is convex. And there's a set of omega that contain all the valid parameters, valid canonical parameters that make things integrable. Okay, now let's connect exponential family with Markov networks. So we know Markov networks, we usually write it as 1 over z and a bunch of potential functions multiplied together, right? And this is essentially in an exponential family form. So if you push everything inside the exponential and then parameterize the log of potential function as a linear function, then it's just an exponential function. For example, in the Gaussian MRF, also appeared in homework 1, we can just rewrite the Gaussian MRF as an exponential form. And we know this is a valid Markov random field because of the Hammerschmidt-Clifford theorem. And in the homework, we proved that the inverse covariance matrix is the sparsity pattern of the inverse covariance matrix under the Gaussianity assumption represents the conditional independence within the distribution, right? So, and that, along with the Hammerschmidt-Clifford theorem, says the distribution should factorize over this graph represented by the inverse covariance matrix. Okay, and if we write the density as an exponential form, then it's just going to be some exponential and then the big theta matrix multiplied by some XX transpose. Here, the XX transpose is going to be our sufficient statistics, and the big theta matrix is going to be the canonical parameter. And anyone know what A is? A is the log partition function. So on one hand, it's going to be the integral of the Gaussian PDF, the exponential thing in the Gaussian. So it's a Gaussian integral. If you write it out, it's going to be something like the log determinant of the sigma or something. Okay. There's another example. Actually, there's even simpler example. Let's consider an Ising model like this, and each variable here is just -1, +1. Then we can write its density as some kind of marginal potentials and then pairwise potentials. Right now, because these are positive or negative ones, and depending on what your model says, you can sometimes say if they are equal in sign, then I give a 1 score, and then if if their signs are different, then I give a -1 in the score. So this is one way to express Ising model in the exponential family form. And the slide here is just a multivariate version. So what if instead of this we have 1 to R? Then we can use indicator variables, or in the modern language it's called the one-hot vector. So the same thing. You can still represent everything in the exponential family form. The inside term is all linear in the natural parameter and the sufficient statistics. So the indicators are going to be the sufficient statistics. And we said we want to infer. What we want to infer in inference task is oftentimes the singleton marginals or the pairwise marginals or the partition function. And those, the reason why we're interested in representing distributions or our Markov network into exponential family is because in exponential family, these things are very nicely represented. So in exponential family, first of all, the marginal parameter, the marginal distributions can be written as the mean parameter. So it's just the expectation of the indicator. And then same thing for the pairwise distribution. And if you take the expectation over the indicators or the sufficient statistics, then it just gives you the mean parameters. So a background knowledge that you might need for this is exponential family distributions have different ways of parameterizing one thing. So one specific parameterization is the canonical parameters, and the other is the mean parameters. So these are dual to each other. They can represent. If you know one, you can convert to the other one that represent the same distribution. And in the context of exponential families, if you convert theta canonical parameter to the mean parameter, this process is essentially performing the marginal inference or the pairwise inference. Okay, and also second thing we know is we try to compute this log partition function. It's also very widely used inference task, and in exponential family, that just represents the log partition function, right? Let's look at an example. So the simplest possible probability distribution is a Bernoulli, and coincidentally, this is also representable in exponential family form. If you might be familiar with this PDF, right? P of 1x and 1 minus p of 1x is for parameterized by little p. But it can be equivalently represented as the exponential family. So p here is going to be the mean parameter, and theta is going to be the canonical parameter in this case. So if you work that out, then the link between the canonical parameter and the mean parameter are going to be something like the thing over there, 1 plus e to the theta over theta. But in the Bernoulli case, because everything is one-dimensional and the functional form is very simple, you can work this out very easily. But in more complicated models, this process of given a theta, you want to find a corresponding mu, is a very challenging task. And that's essentially the thing we want to use variational representation. So we want to write this mu as a maximization of something. Or if we want to know this, we want to write this as maximization of something, and then solve this right-hand side instead of directly trying to get this mu or a. For that, we need to know something called convex conjugate. So this is a very important cornerstone in convex analysis. It's sometimes called the Fanchel conjugate or Fanchel dual or conjugate dual, whatever you call it. Given any function f, you can come up with a dual function, a conjugate function f star, related to the original function in this way. So the functional form may look a bit mysterious, but what it does is essentially, if you look at the first thing, it's theta multiplied by mu. For a given mu, on the left-hand side, we're giving this fixed mu, right? For a given mu, the first function in one dimension is just a linear line that goes across the origin, right? And mu, the value of mu determines the slope of this line. Okay? And then on the left-hand side, we're subtracting, on the right-hand side, we're subtracting the value of f at theta. So what we're essentially measuring is measuring the distance between this line and the curve f. So we're maximizing the distance. So we're looking at this distance. And then, for example, at this point, we're looking at this distance. And we're looking at what is the maximum distance this can take. So in this example, it's going to be somewhere around here, right? And equivalently, if you translate this a little bit here, then it's going to be the value of f conjugate. Okay? And one nice property of conjugate function is whatever f you give it, the conjugate of f is going to be a convex function. To see it, you just need to know it's pointwise supremum of a convex function, or essentially a linear function of mu. So it's a convex function. Another useful thing is if the original function f is convex and satisfies some mild conditions like lower semi-continuous, then the conjugate of conjugate is itself. So you get something like f, you get a conjugate, you arrive at f star, and you conjugate again, you arrive back at original function. So that's a very nice property. And we know now if we come back to the exponential family, we know this log partition function is convex, right? So we might as well plug this a function in f. Then what we have is a variational representation. We've expressed the log partition function a as a optimization problem. And then when we're trying to get a, we try to solve this right-hand side optimization problem, supremum of something. And we'll later see that the maximum value attained at this right-hand side, so the argsup or argmax of mu, is going to be the mean parameter. So we're getting two birds at one stone. So we're both getting mu and a at the same time. So let's see how it works, because we don't know what a star is, right? We don't know what the conjugate of a is. We already don't know a, and how do we know about a star? So that's the problem. So let's work through some examples. It's going to be Bernoulli again. So for Bernoulli, we're kind of cheating because we already know what its a theta is. But let's just, for the sake of exercise, let's plug in the form of a, and then that's going to be the representation for the a star function. And if you try to solve the right-hand side of a star and write down the stationary condition for theta, the optimal theta and the optimal theta is going to satisfy this stationary condition. Mu is equal to something. And then now if we want to come up with a closed form of a star, then we need to plug this theta into the right-hand side of a star, right? So we need to invert this relation a little bit. So essentially, the stationary condition says something like this, and then we need to invert this so that we know theta star is this, right? And then we can plug this theta star in the a star mu is equal to here, right? So let's plug this into theta star here, and that's how we get this dual function. But we need to be careful because we can't just blindly plug this mu in and then call this dual function, because what can break down? Can this mu function here, can this mu take value of 2, for example? Yes, no? For any value of theta, can this value of mu take something like 2? No? Why? Reason? Yeah, right. So, okay, you're the same person, right? You get 1.5 additional points then. Yeah, so it's obvious that mu has to satisfy some range. So we can't defined A star for the entire real values. A star is defined on a restricted value. So A star should only be defined on a very small region compared to the entire real line. So that's what we say here. So mu has to be between 0 and 1, and then otherwise we lift everything to infinity, and that's effectively restricting the domain of A star to be on 0 and 1. Then once we got this A star, then we can plug this A star in the variational form of the problem here. So we restrict mu to be this, and then plug this form. We have this closed form here, and plug in here. Now we can try to solve for A. And the argmax of mu there in the lower problem is going to be our mean parameter, and it checks out easily in this case. So we've been through a very long journey, a very indirect journey of first looking at the conjugate function and then try to write down its stationary condition and then try to identify the region of mu and then write down this A as the maximization problem restricted to that region and then plug this dual function in. And that's the final variational representation we're going to solve. By the way, this is by no means practical. So we're just going through this conceptually and try to unify different group of thoughts, school of thoughts. Nobody's going to go through this practically, right? It's just for understanding purpose. So in the last slide, we've seen for Bernoulli, but in general, the process is, as I said, we try to write down the dual function, and then in order to represent the dual function, we need to the optimal theta should satisfy this stationary condition, and then this stationary condition, if you've written out differently, it's just going to be this mean constraint. So if you write down this stationary condition of right-hand side, then what is it going to be? So sorry, A theta. Okay, if we take derivative with respect to theta, it's just going to be mu, right? And then we know gradient, if we write down gradient of A, it's just going to look something like this. And this is essentially the mean parameter of the exponential family. So it's taking the mean of the sufficient statistics. So that's the definition of the mean parameters in exponential family. So that's why we say the argmax here, argmax of mu, is the mean parameter. So we can get two things at once. Still, we need to be careful because not all mu is realizable. So the set of mu that are realizable is the set of mu that's supported by this constraint, stationary constraint. So we need to be careful what what range of mu we are working with. As in the Bernoulli case, we have to work with 0 and 1, between 0 and 1. So for now, for this moment, let's ignore that. And suppose we've identified that good region of mu. And then let's plug this mu in. Let's look at what A star is going to look like. So if you plug this in, then the mu is just going to be expectation of log p. And expectation of log p is just the negative of the entropy of the distribution. So we have an intermediate answer. It's that, let's see, where is this? So our goal, let's recap a little bit. Our goal is to get mu or A theta. And variational form is to represent A theta as a supremum of mu is to solve this variational problem. And then we need to know what A star is. And we have an intermediate answer there. It's the negative entropy of distribution of this exponential family distribution. Okay? So let's recap a little bit. So we wanted to solve for this, and so we can write down this optimization problem, and and we know this is equal to the negative entropy. But in order to solve for this, we need to be careful. This mu has to also be in some range, and getting this range can be tricky. And also evaluating this negative entropy is also a tricky part. So, as I said, evaluating this is essentially trying to get the canonical parameter supported by this mean parameter. So we go through that by the mean of sufficient statistics mapping. And then once we get this canonical parameter supported by this mu, we can plug this into the negative entropy and then evaluate this dual function. Now it's the time to really consider what set of mu's are supported. So what set of mu's here are valid to define a finite dual function A. And in the context here, it's called the marginal polytope. So let's look at why it's called marginal polytope, or especially why is it a polytope. So recall our definition. We know mu has to satisfy this. Right? But if you expand this expectation, it's just going to be a bunch of weighted average of phi functions. And then we know weighted average of a bunch of functions, a bunch of terms form a convex hull. So let's say this is our phi 1 of x. This is our phi 2 of x. This is our phi 3 of x. Then what are the sets of mu's that are represented by this? It's just going to be everything in here. It's the weighted average of all these 3 points. That's what's represented in the top right. So that's by definition a marginal polytope, and yeah, we have here. So it's a convex hull of the sufficient statistics, and we are treating these points as the extreme points, and then forming a convex polytope, a convex hull. And the theorem says if you have a finite non-empty convex polytope, and you can represent this as a finite set of linear inequalities. So what this is saying is this set here is a marginal polytope, and then this marginal polytope is a convex set. And you can represent this as a finite number of linear inequalities. So one question is, this problem here looks convex, right? It's constrained to a convex set. And then on the right-hand side, you have something nice, linear times linear plus convex. But why do we bother with doing all this approximate inference when we have a convex problem we can solve? Any guesses? It's because I only said it's a finite collection of linear inequalities, but finite is a very vague term. It could be exponentially many. So the number of linear inequalities really matter. And once you go beyond like 2-node graph or 3-node graph, the number of inequalities you need to take care of is going to look crazy. So that's why this problem is essentially intractable. Yeah, in two-variable case, everything is simple. Your sufficient statistic is just the marginal variables and then a pairwise term. And there's only like 4 configurations that can satisfy this. If you put 0 and 0, then the third term is definitely going to be 0, right? So if you write those down, then the endpoint, the extreme points are going to look something like that. And the realizable mean parameters of this 2-variable Ising model is just going to be the gray thing down there. And it can be represented as 4 linear inequalities. But here we have 4, right? And 2 variables we have 4. For 3 variables, we immediately have 16. And this number grows very fast. So the number of half-planes or linear inequalities are also sometimes called facet complexity. Grows super linearly, I think exponentially, but only for tree graph this grows linearly. So that's why that's one of the underlying reasons, very deep reasons that we can perform inference efficiently on tree graphs. It's because the facet complexity is linear in the tree. But for general graphs, we don't know how, it's very hard to characterize this marginal polytope. So that's where this variational principle comes in. So as I said, we define this conjugate function, and then we write this, our quantity of interest into a variational form, and we write down this marginal polytope. And in the two-variable Ising model, this negative entropy has a closed form like this. And we can just plug this closed form in the original variational problem. Then once we solve this newer, lower variational problem, then we essentially obtained a optimal mean parameter. Okay, so here's what the 2 different methods I mentioned earlier. One is mean field method, and the other is the loopy brief propagation differs. So we have this unifying view of inference problems as this variational equation. So we want to get A, and we try to express this as a variational problem. And what mean field does is to replace this marginal polytope M with something called inner approximation. So if the marginal polytope looks something like this, and what mean field does is it tries to form a inner optimization problem, inner set. So let's call this M hat. What mean field is doing is essentially replacing M with M hat. And then what loopy BP corresponds to is to replace this M with something upper bounds this marginal polytope, and then use some corresponding entropy approximation for A star. Okay, let's briefly discuss the mean field approximation. I think we still have like 7 minutes. So what mean field does is it has this original graph in the middle, and then one thing you can do is you basically ignore all the edges and come up with a different graph with all the nodes, and none of the nodes are connected to each other. In terms of canonical parameter, it means we are setting all the edge pairwise canonical parameters to 0. So the set of canonical parameters we consider are much smaller now. Or on the other hand, we can also form a tree graph, and we know the exact inference on tree graph is efficient. So these are 2 options. Okay, so now for a new set of canonical parameters, because we've reduced from original sigma to something smaller. What is it called here? Sigma f. Okay. then what is going to happen for the mean parameters? Is the set of MF going to be become larger or smaller? Anyone? Remember, the set of the constraint set M is the set of realizable mean parameters, and by realizable I mean for distributions parameterized by this thetas in this set. So the reasoning is going to be, if we form a smaller canonical parameter set, the set of distributions parameterized by this is also going to be smaller, right? So the set of distributions we consider are going to be less flexible. There are less distributions we can play with. So the mean of those distributions are also smaller, are also fewer. So we're considering fewer distributions, so there are fewer mean parameters we can realize. So the set of M of F is going to be a subset of the original marginal polytope, and that's why we are calling this an inner approximation. So essentially, the mean field solves a relaxed problem where we just replace the original constraint set M with the inner approximation constraint. So one example is just a naive mean field. So given the Ising model, and if we ignore all the edges, like we don't preserve any edges or any trees, we just do the variables alone, then the resulting graph is going to look something like below, and we can go through the same process again and form the marginal polytope. This time, the marginal polytope is going to be much simpler. So the dual, and also under this approximation family, because the distributions don't have any interaction terms, the negative entropy is just going to be a multiplication of individual marginal terms. So that's what the final line says. The dual, recall the dual is just a negative entropy, so the dual decomposes. If you take the log, then it decomposes into a bunch of sums of individual terms. Okay, so if you work this out, then you arrive at this naive mean field update for Ising model. You can come up with this algorithm from a completely different path, but this is the unifying way of looking at everything, and so it's very nice. And also, because we said this is an inner approximation, so the optimization problem here, we are restricting it to a smaller set, right? So this is gonna, the approximate answer we get is gonna always be smaller than the true answer. So that's why we are lower bounding the log partition function here. Okay, as I said, the geometry of mean field is just a inner approximation. It's preserving all the extreme points because you can always realize the extreme points, and by realizing a distribution with only one indicator and all the others are 0. And you can also prove that there are these two sets are different, so there should be some points non-empty, the regions between these two sets. So that's why the inner approximation is definitely going to be non-convex. Okay. I think we don't have time, so let's skip loopy BP. So, but same principle applies, and this is just some different kind of approximation for the constraint set M and the dual function or the negative entropy term. And once you work it out, then the messages or the BP updates you derive are going to be the Lagrangian variable of this optimization problem, which is very neat. So the alpha beta messages you derived in the homework actually can be interpreted as the Lagrangian variable of the optimization problem there. So this is very nice link conceptually. And the BP approximation is, as opposed to the mean field, is going to be an outer approximation. Okay. So yeah, so the second part of the lecture, we covered the unifying principles behind variational inference, and we talked about, we represented the exact inference problem as an optimization problem, and then we looked at why it's hard to solve and in what cases it's easy to solve, and what we do when it's hard to solve. And there are basically two ways you can do when it's hard to solve. One is to form an inner approximation, which corresponds to the mean field approximation, and one is to form an outer approximation, which corresponds to the loopy BP. Okay, I think that's it. The next lecture, we're going to move into sampling methods, like simple Monte Carlo to importance sampling, and Markov chain Monte Carlo, and hybrid Monte Carlo, and so on. Okay, thanks so much.